Hello, everybody. Mr. Lake here, and today I'm going to be talking about atomic emission spectra. What is that? So, different elements emit different colors, not usually spontaneously. If you just have a sample of hydrogen, it's not like glowing with a certain color. But if you excite it with like electricity, if you run electricity through it, or if you shine certain wavelengths of light on it, it will start to emit its own wavelengths of light and emit certain colors. And different elements emit different colors. Here's a great example. Okay, no dancing, Mr. Lake. As you can see, each of these glass tubes that this person is holding has a different pure element in it. Gas, it's and they're sorry, they're gases, right? So there's hydrogen gas, helium gas, neon gas, argon, krypton, xenon, and nitrogen or neon. No, nitrogen. And the person put a Tesla coil, or basically a source of electrical current, behind these tubes. And when a tube comes in contact with that electrical current, the atoms of that element start to emit light. And you can see that the different elements emit different colors of light. Neon is like orange. Krypton is this crazy blue. Xenon is this kind of dull blue green. Neon is, or nitrogen is purple. Different elements emit different colors. This is called atomic emission spectra. To understand why this is, I need to explain the concepts of ground state versus excited state for an electron. We're still talking about electrons here. So, a couple of videos ago, I told you about orbitals and how electrons tend to exist in these clouds, these spaces surrounding the nucleus of an atom. And those spaces kind of are split up into um, different levels. So, there's like going to be an orbital here, and I apologize, I don't have my drawing pad plugged in, but there's going to be some orbitals at this level, and then there's going to be more orbitals at the next level. Ooh, this is getting real pretty. Real pretty. A plus work, Mr. Lake. Okay. So let's say that an atom has electrons that exist in these orbitals, these energy levels, right? So maybe there's, and I'm just going to draw dots, even though we know that electrons are not dots, but I'm going to say there's, some electrons in these spaces here. And I'm not drawing the correct number of electrons. I'm just, and then maybe, there's electrons in some of these spaces here, right? So there's some electrons, and they're just chilling out. And they exist in the level in which they belong. That's called their ground state. You can think of it as like the position of rest for an electron. If it's just hanging out in an atom, it's in its ground state. It's just chilling. But it is possible that when atoms are exposed to energy, usually in the form of heat or electricity, sometimes even like laser light or something like that, when atoms are exposed to energy, their electrons move. They move specifically between orbitals. And so this electron right here might basically absorb some energy, and suddenly now it's in this orbital here. It like jumps up into the third energy level, and it's not supposed to be there, right? It's ground state, its resting state is in the second energy level, but it just jumped up into an orbital in the third energy level because what we haven't really talked about is that each of these orbitals is associated with a certain amount of energy or a certain energy state. And so if an atom or an electron suddenly absorbs a bunch of energy, it doesn't really fit into the orbital that it was in. So it's got to find a new home that it's bigger and is associated with higher energy where it can exist. So it jumps up to a higher energy level. Here's the thing though, it can't last. It's the age old, it's not exactly a law of physics, but you could pretty much say it is. What goes up must come down. in a situation where there's gravity. But, if I throw something up in the air, it's not going to stay there. It's going to come back down. And so it's kind of the same thing with electrons. If an electron is excited up to a higher energy state, an excited state, it will inevitably fall back down to its state of rest. It can't just hang out there all the time. And when it does so, the difference in energy between the excited state that it was at and the ground state that it's returning to, that difference in energy is released all at once as a photon, which is a particle of light. I'm covering a lot of different things in like a few sentences here. So, electrons jump up to an excited state and then they fall back down to their ground state and they release energy in the process. And that energy is in the form of light or sometimes a different form of electromagnetic radiation because light is just one type of electromagnetic radiation. So, it could be releasing a microwave or a gamma ray or an infrared wave or an ultraviolet wave. All of those things are the same type of energy, which is electromagnetic radiation, just like light. But we're going to focus on light. So electrons move around, they jump up, they fall down, they release light. Different elements, interestingly enough, have kind of different signature ways that they do this. And we call these signatures atomic emission spectra. So for example, let's take a look at hydrogen here. Hydrogen has a tendency for its electrons to jump up to excited states and then fall back down to ground states in a way that releases these specific wavelengths of light. Several wavelengths in kind of the purple range, a blue, a light blue getting towards green, and then a red wavelength. And hydrogen always does this. So if you light up a hydrogen sample, it's going to emit these wavelengths of light and not really any other wavelengths of light, which is why, going back to that video I showed you at the beginning, that's why hydrogen had a certain color to it, is when you emit only certain wavelengths of light, it's going to appear to have a certain color. Now, helium is different, right? Helium emits some of the same or similar um, violet frequencies, but more in the blue range and different wavelengths of blue light. And then it releases a yellow wavelength and then a slightly different red wavelength. And neon is very different. Neon emits no purple, some blue, a little bit of green, and then a lot more yellow, orange, and red than hydrogen or helium, which is why you might remember the neon sample was like orange, whereas some of the others were more blue, right? Hydrogen and helium are going to be more sort of bluish, neon's going to be a lot more orangish. Again, sodium, mercury, every single element has a different unique atomic emission spectra. So it's like a fingerprint. It is a recognizable and identifiable visible signature for an element. Pretty awesome. And these are useful in a bunch of different ways. First of course, if you wanted to try to identify what was in a sample, like let's say you had a sample of a gas and you wanted to know what elements were in that sample, well, you could just try running electricity through the gas, as long as you do it in a way that doesn't ignite the gas if it's flammable. You could run electricity through the gas and you could see what wavelengths it puts out. And based on what wavelengths it puts out, you could probably identify what gases are in there. And you can even do this if the sample isn't pure. So let's say there's 6 different gases that are in there. You could still excite all of the elements, gather a full atomic emission spectra, and then just use a computer or use your own knowledge if you're really good at this to identify like special wavelengths, signatures within the signature that will tell you that certain things are there. Like for example, I'm talking about like, you know, this this wavelength right here, right? That is slightly different than any other wavelength of any mercury comes close, but this is a slightly different wavelength down here. This wavelength right here, if you see that wavelength, you might be like, that signifies that there's probably some neon in the sample. And if you're seeing a lot of this frequency as well, you're probably going to think, okay, neon's definitely there. So it can be used to identify unknown things in a sample from soil or a medical sample or uh, a forensic sample or whatever kind of sample you want to use. This is called atomic emission spectroscopy, spectronomy, one of those two, and it's an actual technique that people use. It is also useful for identifying the movement of distant stars. What? Stars are really hot, right? And one of the things we established was that if you excite electrons in an atom with heat or electricity, they will emit wavelengths of light. Well, there's enough heat in a star to cause this to happen in the elements that are within that star. So let's say a star is full of helium, for instance. Well, that helium is going to be very, very hot. It's going to be absorbing a bunch of energy. The electrons are going to be constantly jumping up to an excited state, falling back down to a ground state, and emitting light. So that star is going to be emitting a whole bunch of this. And that light, I mean, if we can see a star, if it's a pinpoint of light in the sky, that's enough light that's reaching us from that star that we can study that light. We can gather samples of that light. We can study it using instruments and figure out what is there. So we can, first of all, identify the composition of that star. We can say, oh, it's probably 80% helium and 20% this other thing or whatever, right? In addition, there is something called the Doppler effect, which you may have learned about before. Maybe you've watched The Big Bang Theory when Sheldon dresses up like the Doppler effect for Halloween. But essentially, the Doppler effect is where wavelengths and frequencies of things change based on movement. So I'll try and kind of like simplify it for the purposes of this video. We might get back into the depths of it later, but if a star is moving towards us, all of the frequencies of light that it emits are going to be slightly shifted in the blue direction. And it's because those waves are getting compacted in front of the star that is moving in front of us. But basically, all of these lines in this sample or this atomic emission spectra would be shifted to the left a little bit. So if we know what the emission spectrum of helium is, and we can say like, well, that's the atomic emission of spectrum of helium, except that it's shifted a little bit towards the left, we can say that star is moving towards us. And depending on how far it's shifted, we can say that star is moving towards us at this speed. So a star that is billions of light years away, if we can gather light from it, we can tell what it's made out of and in which direction it's moving and how fast. And if it's going away from us, then its exact opposite, all of the frequencies are going to be shifted a little bit towards the red. It's called redshift, and everything's going to be a little bit lower frequency. So that is a kind of crash course introduction to atomic emission spectra. I hope you enjoyed this video. Hope it was interesting, taught you something, and I will see you in the next one. Take care, everybody.